Welcome everyone watching on YouTube. So this is our 106th or 107th live stream geometry. I'm not sure, but we have 3 other people here with me right now. And today I'm going to go through problems from the ELMO math contest. So this is a math contest we did. We've done it on our channel before, and I might have done these problems before, or at least some of them. But they're usually really elegant problems. And I believe Evan Chen runs the contest. I'm not 100% sure, but I think he at least plays a big role in making the contest. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. U.S. Central Time. So my email, mgreenb801@gmail.com. It's in the description of my video. All right, so I will start sharing my screen. So here's the first problem. So this is from the 2019 ELMO shortlist. We have the triangle ABC with altitudes BE and CF, and they meet at the orthocenter. So Abdulahil showed me that if I use a certain desktop version of GeoGebra, I could make tools that would like automatically create the altitude, so I wouldn't have to do it. But I'm still working through that. So for now, I'll just draw it like this. All right. Let me delete these. Yeah, that'll allow me to create problems much quicker once I set that up. So they meet at H, and then you reflect A over BC, and that's A prime. All right, so that's A prime. Obviously, these are collinear. I'll just leave it like that for now. Then we draw the circumcircle of ABC, and we see where does it meet A prime AE and A prime AF. So kind of an interesting configuration. Okay. So it meets A prime AE at P, and it meets, this circle meets it at Q. And DC meets PQ at R, and we want to show that EF is parallel to HR. That's interesting. So this is R. And this is another thing, once I create the tools with GeoGebra, I might do it where it only does like a line segment up to the intersection point, because that's something I use a lot. Okay, so we want to show EF and HR are parallel. We'll draw this point right here. So go to the altitude. And let's see what we can do from here. Maybe shrink the diagram just a little bit. Something like that. It's a cool problem. Let's see. I draw this. This triangle is a reflection of triangle ABC. It almost looks like R is the center of the circle, but it can't be, or I highly doubt it. Yeah, it's not true. So maybe it's worth drawing the centers of these 2 circles. It's going to lie on both are going to lie on BC. that center is really close to point F. So let me make it a little farther away. Maybe something like that. So G is the center of that circle, and I is the center of this circle. Make it a little bit of a taller triangle. Something like that. I wonder if HR is, oh no, I was going to say maybe it's tangent to this circle, but it can't be because the tangent is horizontal. Just draw it a little like that. I actually don't remember doing this problem before. I think this is the first time we've done this. I wonder, let's try something. I wonder where EF, so EF and BC meet at a point. Is PQA prime D cyclic? No. So this feels a little bit like projected geometry.
HR is tangent to BHC.
Okay.
It is sufficient.
Oh, and BHA prime C is cyclic.
It solves the problem because, yeah, it solves.
But
because, oh, sorry. We have to prove the tangent, and that solves.
yeah, if we prove it's tangent, then it solves the problem.
Yes.
It's a good observation. We know this is cyclic. And yeah, so this point right here is the orthocenter. J is the orthocenter of A prime BC. I don't know if that helps. It looks a lot like the radical axis theorem might help. And we'd have to find some circle. These circles almost look tangent. Let's check. I don't think it's likely they are. Yeah, these circles look tangent. Interesting. So yeah, can we show those are tangent? Because then maybe we could use the radical axis theorem.
Yeah.
So we have these two circles, and then we have this circle and this circle, and that's PQ. Yeah. So if we show these are tangent, that would solve the problem. PQH, and BHC. yeah, what's the best way to show two circles are tangent? Maybe we could use inversion somehow. So yeah, what's a good center of inversion? What would happen if I inverted about that, just the circumcircle of ABC? So H would go to H prime all the way over there, and P and Q would stay the same. So we would want to show, I don't know if this really helps, but we would want to show these two circles are tangent. You know what? What if we invert about this circle? So let me think about this. Or no, what if we do an inversion with radius square root of AF times AB? Because AF times AB equals AH times AB equals AE times AC. So it would send B to F, C to E, and H to D. So basically it would send the circle BHC to DEF, which is the 9-point circle. And then for this circle, where would it send Q to? Q and P. So Q is so this circle, it sends to line EF, I believe, right? And this circle right here, what would it do to this circle? So A goes to the point at infinity. E goes to C, and where would A prime go to under that inversion? Let's think about this. So one of the circles will go to the 9-point circle. Trying to figure out how do I draw. What would the A prime go to? So D goes to H. So A prime is twice as far away, so it would go to the midpoint of AH. So that so it would go to K. So we just have to show that DEF and K so A prime, let me think about this. So this circle A prime P, A prime goes to K. Well, P is the intersection of two circles. So this circle centered at, so E goes to C. So it would be K, it would be line KC, I think, right? Because A goes to the point of infinity. Okay, so that goes to line AKC. So it would be the intersection of CK with okay, now I'm a little confused. CK with EF, so maybe it's this point right here. Is this point L or something? And then let's draw BK. And it intersects that line at this point. So maybe we need to show. So we're saying the circle PHQ goes to DLM. Is that right? And we need to show those are tangent? I don't know if that's right. I might have made a mistake. Oh, yeah, I think it is actually equivalent to saying that. So, yeah, those look tangent at D. I don't think there's another intersection point. Okay, that's kind of interesting. I don't know if that makes the problem easier or harder though. That's the thing. So we want to show the 9-point circle is tangent to DLM, where L and M are the intersections of CK and BK with EF. Yeah, so I don't know if that makes it easier or harder. All right, looks like we have someone else joining from Germany, I believe. And he's still connecting. Hey, Roland, thanks for joining. So we're on our first problem. We added a little bit to the diagram, but the original problem was, so I could hide all the stuff we added. But we reduced it to another problem. So if K is the midpoint of AH, where H is the orthocenter, and we draw L and M like this, so where BK and CK meet EF, then we want to show the circle DLM is tangent to the 9-point circle. So that's what we figured out. The original problem is equivalent to that. So yeah, you could try a different way to solve the original problem, or you could try to show that. So you could draw the 9-point center. That's nice. It was called N. I wonder if showing these are tangent is equivalent to showing angle FDM equals angle EVL. So let me check if that's true, but I think there's like a lemma that says that those are equivalent. Yes. So if we can show angle FDM equals EVL, that would solve the problem, I believe. And by Blanchett's theorem, we know FBB equals EBC. So that's the same as saying that, showing that angle BDM is CDL. And I think that might just be projective geometry. It's also equivalent to showing that CM and BL meet on altitude. Yes. And we know, I think we know that's true because that's equivalent to saying that, yeah, that's true because these 4 points are in harmonic conjugation. So yeah, I think I've solved the problem. It's an interesting solution. So I'm going to draw the intersection of EF with BC and see what it's called. Let's call it P instead. So I used inversion. This is one of the few times where I use inversion on my own successfully. So let's write it up. Okay, so yeah, we don't need to show the whole thing. Okay, so, oh, I don't want to call it P because this was P. So let's call it T. And then we can call this P again. Okay. So first BHCA prime is cyclic by symmetry. So I'll say by reflecting over line BC, we find BHCA prime is cyclic. Okay. And we want to try to show that the circumcircles of PHQ and BHCA prime are tangent. And we're going to invert those two circles about the circle centered at A with radius AF times AB, or square root of that. So I'll say invert about the circle with center A and radius square root of AF times AB. So the inversion swaps F and D, H and D, A prime and K. So here's what the inversion does. The inversion swaps F and B, E and C, H and D, and A prime and K. Okay. So basically that means it takes the circumcircle of AB to the line EF, and it takes the circumcircle of AEA prime to the line CK. So thus it swaps ABC and the line EF, and also it swaps AEA prime with the line CK, and AFA prime with BK. I should clarify probably, I don't know if it's that obvious, but let K be the midpoint of AH. Okay. And then, okay. So therefore it swaps line PQ with line LM. Or it swaps the circle PQH with LM LM, the circle LMD. So thus it swaps P with L. I think it's P and L, right? Yeah. P with L and Q with M. Okay. So we want to show that these two circles are tangent. And so by the inversion, it's the same as showing that these two are tangent. And we're going to show that's not too hard because we're going to show FDM equals EDL because angle BDF is CDE and also BDM is CDL because of harmonics. So let EF meet BC at T. Then BC DT is harmonic. And that implies that BL and CM concur on KD. So by Blanchett's theorem, BDF equals CDE and BDM equals CDL. So I'll just say that in the other order. By Blanchett's theorem. So we'd have BDM equals CDL. And BDF equals CDE. And that implies that angle FDM equals EDL. All right. And that means that the two circles are tangent by a certain lemma. So I don't know if you guys have seen that lemma, but if FDM equals EDL, then these two circles are tangent. By a well-known lemma, this implies the circles FDE and MDL are tangent. And then by applying the inversion, then we have HPQ and BHC are tangent. And then once we know that, it's not hard to show that EF is parallel to HR because basically the angle that angle RHB would equal angle HCB, which is HEF, so then they'd be tangent. So angle RHB equals angle HCB, which is angle HEF. Sorry. And that implies EF is parallel to HR. This is a fun one. Maybe, I don't know if we needed to use inversion, but it works. Anyone have any questions on this solution before I move on? It's a good one, right? Yeah. All right, so I will move on to the next problem. All right, so here's the next one. Also from the ELMO, we have a triangle with end center I and circumcenter O. And we draw the end circle and the antipode of A. Okay. So this should be O. This is almost like a right triangle, so let me make it more cute. And here is the antipode. And it's already called A prime, and we need to draw the end circle. And we'll let I be the center of it. So this is D, E, and F. And I is the center of C. Or maybe it's the center of E. Yeah. All right. So then we draw the circumcircles of ABC and A prime EF. This is interesting. A prime EF. So let me draw this diameter here. This feels like another problem that might use inversion because it has like the intersection of circles like this. So they meet at G. And the circumcircles of AMG. So M is the midpoint of EF. Okay. Let me draw that segment in. So this is M. I don't know if it's worth drawing the whole angle bisector, but obviously AM and I are collinear. So let's wait a second. Prove that if GH, what is H? So these circles meet at a point H, AMG, and A prime EF. What am I doing here? Okay, so this point right here is H. It's very close to point M. And then GH and EF, they meet at T. And then, okay, so this is like the Sharkydevil point. I don't know if you guys have seen my video on that, but this point right here has a lot of properties. And I don't remember all of them. But I would say the most famous property of this point possibly is that we draw this circle, then this would be collinear with T and I. Well, if we can prove that, J, T, and I are collinear, then that would solve the problem. And yeah, it's true. Or we could prove that A prime, T, and I are collinear. It's like the same thing. So I'm gonna just draw the angle bisector. I don't know if it'll be helpful, but just in case. Because yeah, then the problem is also equivalent to showing BT is parallel to AK. So a lot of different equivalent ways of looking at it. All right. So this feels a little like the radical axis theorem, right? Oh wait, does the radical axis theorem trivialize it? So we have the radical axis theorem on this circle, and this circle. That would say that these pass through T. And is that the altitude from A? It almost looks like it, but I'm not. That does look like the altitude from A. So we know angle ALI is 90 degrees because AI is the diameter of this. Can we show that this is the altitude actually? Because yeah, then we don't need this line GH. Then that's just the intersection of the altitude with EF. If that's true. Let's check that it really is the case. Oh, it's not the altitude. It looked like it, didn't it? But yeah, it's not. Okay. So I wonder if there's something special about AL. Does it pass through the mixed linear point of tangency of the mixed linear incircle? Let's see. So actually, I don't think it does. I think it's very unlikely that it does, but I'll check it. So that would be the same as saying that, so yeah, it doesn't. But there might be some other stuff. So yeah, actually, it's a well-known fact that J, D, and K are collinear. So I proved that in my video on the Sharkydevil lemma. So yeah, can we use the radical axis theorem on a circle through Oh, is JIHG cyclic? Because then maybe we could use the radical axis theorem there. If that's true, that let's try to show that that's cyclic. JIHG. So JH equals JG, right? Or wait, is J the center of the circle? So this is the circumcircle of AMG. First of all, okay, J is not the center of that circle. So we can't assume that. What was I trying to show? I was trying to show that JHIG is cyclic. How would we do that? Can we use power of a point from K? That seems, well, but it doesn't pass through H, so that makes it a little hard. Actually, I think if we could show that cyclic, it would solve the problem, because yeah, then by the radical axis theorem, JT and I are collinear, I think. So maybe we could use inversion. So let's see. If we could try this. No, I don't think that does much. We could try this. Or we could try an angle chase. Let's try inversion. So how should we invert? So AM times AI is AF squared. What if we invert about the circle with center A and radius AF? So it would swap M and I. E and F would stay the same. So this circle, M would go to the point at infinity. I'm sorry. A would go to the point at infinity. M would go to I. Where would G go to? So we could try to see where this circle goes to. But I don't know where B and C would go to, that's the thing. For this circle, E and F would stay the same. I don't know where A prime would go to. But I like that idea. So like what I would do, so I'd have this circle, and let's see where G goes to. G would go to G prime. A prime would go to, and it looks like G prime lies on this line, so we can check that. A prime, it looks like goes to this intersection right here. It looks like those are all collinear. So basically, it looks like G goes to the intersection of this with JI. So yeah, I think, so we wanted to show that JHIG is cyclic. Where does H go to? Let's see. If I reflect H, goes to this point H prime. So G prime, H prime, I, and it's the same as showing G prime, H prime, IJ is cyclic. I wonder if those all lie on a line actually. So it looks like they do. And it looks, yeah, so there's just so much going on here. Yeah. I don't even know where to begin. But I feel like this is a good idea. So let's see. I just have to prove stuff in the right order. So first of all, maybe I should just hide this point T for now and like draw. Here's how I think I should do it, because we know a lot about the Sharkydevil point. So what I think I should do is I should so the way the problem defines T, it lets GH meet EF. I don't think I should define it that way. I should let T prime be the perpendicular from B to EF. Then I should draw everything else after that. I think I like that better. So okay, so if that's the case, then by all the Sharkydevil stuff, we know that those are collinear. We want to show that G prime and H prime lie on this line. Okay. So let's think about this. So first, can we show the inversion of G about this circle lies on that line? How do we define G? So where does this circle invert to? So the circumcircle of ABC. Let's see. If we invert the circumcircle of ABC about this circle, and then it goes to this line. Interesting. Is that obvious? So where does B invert to? Interesting. So B and C. Yeah, I feel like we're close to a solution. I just need to show that B and C invert to a point on this line. So I could start out by drawing this circle with center A and radius AE equals AF, and then like here is the radical axis of these two circles. Let me hide this point for now. Can I show that the line BC inverts to the line PN? Is it obvious? I guess one way I could do it is I could look at quadrilateral BFEC. that's not cyclic, so that won't do much. So can I show that AQ times AB is AF squared? And then that would mean that this is cyclic. I think triangle AQN is similar to ABN, so I think that would prove it. And I think that is just an angle chase. Yeah, okay. So B inverts to Q, C inverts to R. So the line BQ inverts to, I mean, the line BC, the circle BCA inverts to this line. And then, so G is the intersection of that and A prime EF. And A prime, where did A prime invert to? We want to show it inverts to this point. So it's also going to invert to, by the same logic, it's going to invert to a point on this line. And so but we don't know yet that it would lie on that circle. Okay, so yeah, I think there's like enough to solve this problem. It's just a matter of writing it out. Let's see. So we want to show A prime, H, M. So A prime, H, M is cyclic, but H is, there's just so much going on here, it's confusing me. A, M, G. Oh, we want to show A prime, M, G is cyclic. But if you do the inversion, that's the same as saying that A prime I and the inversion of G are collinear. So we want to show the inversion of G. So everything on this circle lies on the, when you invert it, it lies on the line PN. So yeah, I think I've solved it. I'm just yeah, getting a little confused. Okay, so let me write it up and then you guys can tell me if I'm making a mistake. That would prove that this has to lie on the line PN. Okay, so I'll call this G prime. But basically, so let P prime be the foot of the perpendicular from B to EF. Say altitude. By the Sharkydevil configuration, J, I'll say let J equal be the Sharkydevil point. And sorry, let me see who's still on. So by the Sharkydevil lemmas, or by the Sharkydevil configuration, J, T prime I, and A prime are collinear. Okay, and then we're gonna define Q and R as, so draw the circle with center A and radius A equals AF. I'll let it meet AB and AC at Q and R. And then by an easy angle chase, we have angle ANP is equal to angle ABN. And so triangles AQN and ABN are similar. So I guess I'll write it out. Angle ANQ is half of arc AP. Which is half of arc AN, which is angle ABN. And that means that ANQ is similar to ABN. And that means that AQ times AB is AN squared. And now we can do the inversion that I mentioned. So consider an inversion about omega. So it swaps B and Q and C and R. So it takes the whole circle ABC to the line QR. And that is pretty important. So it swaps B and Q and C and R. Thus, it swaps ABC and the line QR. And so it takes G to a point G prime and A to a point A double prime on QR. It takes G and A double prime to points G prime and A double prime that lie on QR. I think this is all right so far. So now we want to see, so it swaps M and I. I'll put that here. C and R and M and I. Okay. And we want to learn more about, we want to see where it takes, okay, we want to show GHIG, JGIH is cyclic. So how did I do that? Let's see. So that was the original idea, right? forgot what I was doing. Thought I had it. So we want to learn where does, so G goes to G prime. So the circle AMG goes to the circle AIG prime, but we didn't draw that yet. So if we have AIG prime, let's see, A prime EF goes to A double prime EF. Oh, and is A double prime EFG cyclic? I think so, because their inverses, that would be FE A prime G is cyclic. Yeah, so FE A prime G is cyclic. So those points are cyclic. Okay, so H is the intersection of this circle and this circle. So H prime, let's see, M goes to I. Okay, so this circle goes to this line through J, T, I, and A prime. And so, therefore, G prime has to pass on this line. So we know G prime lies on this line. I just don't know where J inverts to. So J, so this circle right here, what does that circle invert to? It should be obvious. I just can't think of it right now. So this circle inverts to line EF. Yeah, because the EF are fixed. So it would be the intersection of EF with PQ. That's where J would invert to. And it looks like it lies on this. So showing that JHIG is cyclic, it's the same as showing that this point M G prime, this point M G prime, and the inverse of H. So this would have to be like the inverse of H. Okay, so basically we want to show H inverts to the point on this line. This is sorry, this is so confusing, but I think it works. Yeah, so all right, let's hold on a second. So much inversion, right? Okay. So G prime, first of all, we want to show it lies on this, which it does because AFE, A prime FE, hold on. So E and F are fixed under the inversion, and A prime goes to A double prime. Okay, so it would be the intersection of this circle with, yeah, how do we know G prime Okay, so we know G prime lies on this circle. We also know it lies on this line. We have to show it lies on this circle. But what is this circle? No, I'm gonna delete that circle. Okay. So AMG and AEF meet at H. So we haven't yet shown that H lies on this, but first of all, it lies on this, which inverts to this. Okay, so we know H prime lies on this circle. And what else do we know about it? We know it lies on we know it lies on, okay. So we want to show that, so we know G prime. Okay, it lies on the line G prime I. Okay, so G prime lies on QR, and it lies on this circle. Oh, we need to show G prime lies on this segment. Okay, so we know J, T, I, and A prime are collinear. We need to show G prime also lies on that. And I think that's true because no, that's not that obvious. We need to show G prime lies on that. But I think it might not be that hard because that's the same as showing angle AJG prime is 90 degrees. And what does J invert to? J, okay. So wait a sec. Does that mean this is 90 degrees? Yes, it does. Okay, so basically we need to show, oh. So yeah, we need to show that J inverts to S, where S is the intersection of EF and PN. And I think that shouldn't be too bad. So we need to show AJ, EF, and PN are collinear, and I think that might just be the radical axis theorem. So AJ is where we have these two circles. EF is where we have these two circles. Let's see. So we have this circle, and the little circle. So this circle ABC and this circle. So that would be AJ. Where do we get EF from that? Because that's the little circle in this circle. Okay, so yeah. So by the radical axis theorem, AJ, PN, and EF meet at a point S. And that point S, you would want to show it lies on the circle. S. And then could we show that that point S lies on this circle? Whoops. So we'd want to show ASG M is cyclic. But so we know AMS is 90 degrees, but we don't know that AGS is 90. That's actually what we want to prove. We want to prove AGS is 90 degrees.
A is 90.
What?
A double prime S.
A double prime S is 90. That's a good point. Yes. So A double prime S is 90. So that implies that that's cyclic. Yes. So AMS equals 90. And that means that A double prime HMGS is cyclic. It's cyclic. And so then that means that S. Okay, so what did I want to do after that? I think I was super close here. So that means that we wanted to show J inverts to S, right? But this circle intersects to line PQ, and this circle inverts to line. Wait, this circle inverts to line EF, and this circle inverts to line PQ, so J inverts to S. J inverts to S since AF inverts to EF and ABC inverts to PQ. Okay. And so I think we're really close here now. Because what did I have to do? I needed to show that JHIG is cyclic, which is equivalent to showing that SH prime G prime M is cyclic. Sorry, I probably got one of those points wrong. We want to show S H prime M SH prime MG prime. We want to show that that's cyclic. So wait, I wanted to show that this was cyclic. I tried to invert. Now I want to show that this is cyclic. All right, see you next time. Thanks for joining. And let's see. is it obvious that that is cyclic? So H prime is the intersection of this circle. How do we define H prime? Just the intersection of these two circles. Oh, but H prime we know lies on this. We wanted to show that. And so I think that helps prove it. I am just so confused because, wait. Because H lies on this circle, which inverts to this circle. So A prime, okay, so I thought I had it, but now I lost it. So we wanted to show G prime light on this line. But we know this line inverts to PQ. So since G prime lies on PQ, then I am just so confused. All right, let's try to work backwards. I'll spend just a couple more minutes on this. So what do we want to show? We wanted to show that JHIG was cyclic. And then, so we try to invert those points, and we got S, M, G prime, H prime. We want to show that's cyclic. And we want to try to use the radical axis theorem to show that this is cyclic. So let's see, G prime and H prime, they lie on this circle. So G prime I times I, they lie on this circle. And S and M lie on this circle. Okay, so ST times TM equals ST times TM. Oh, do we know that HT prime and G are collinear? I think that's what we want to prove. So, but H prime, G prime. So yeah, what does T invert to? No way, T doesn't invert to that. We want to invert T prime about this circle. We want to show T prime inverts to L. because then A, T prime, and L are collinear. And I think that we can show that that might actually solve it. So let's see. So T prime, it lies on EF. I want to show it inverts to L. The line EF inverts to the circle AEF, and this line inverts to this circle, I believe. Yes. So actually, I think we might have made this proof more complicated than it needed to be. So we can show T prime inverts to L because since EF inverts to the circle AJEF, and JA prime inverts to SA double prime A. Okay. So this means that A, T prime, and L are collinear. And once we know that, then I think we can kind of just use the radical axis theorem to show that GHIJ is cyclic. So I think there's a lot of extra stuff that I didn't need really. I don't think I needed G prime. I don't know if I needed G prime. I don't know if I needed Q. I don't know if I needed Q and R actually. Did I? Maybe I did. Maybe I needed Q and R. Anyways, I'll just leave that. Okay, so A, T prime, and L are collinear, and therefore, yeah, now we can just use power of a point. So G T prime times T prime H is equal to A T prime times TL. So and that is equal to J T prime times T prime I. Oops, sorry. And that means that GJHI is cyclic. And that means once we know that, GH and EF. I think actually once we know these are collinear, it implies T prime equals T. We don't even need that this is cyclic, I don't think. So we don't need that, it's cyclic. We don't need that. This is cyclic. And I think everything else is okay. Let's read through it one more time, then I'll move on to the next problem. So, but let's add everything as we learn it. So, actually forget that. So, okay, T prime is the foot of the altitude. We know J, T prime, I, and A are collinear. I don't think we need H prime, so I'm going to get rid of H prime. And then so we have this angle chase, so the inversion takes ABC to this line, because it takes B to a point on that line, C to a point on that line. Okay. So it takes G and A double prime to 2 points on that line. I don't know if we need, do we need G prime? I don't know if we need this circle right here. And I don't know if we really need G prime. So I'm going to delete it. So yeah, we don't need G prime, but we still want this. And so by the radical axis theorem, AJ, PQ, and okay, so we have this circle, the circle ABC, this circle, and this circle. They meet at EF, AJ. Okay, so they meet at a point at S. And then A double prime S is going to be 90. And A MS is 90, so that's cyclic. Do we know this circle passes through H? I think by definition we do, because it lies on AMG. But do we know that? So we know A prime, A double prime, M, and S are on a circle. How do we know that G and H are on that circle? Let's see. So A double prime, MS is cyclic. How do we know H lies on it? And how do we know?
What is H?
H is the intersection of AMG and A prime EF. So how do we know G lies on it? That's probably a better question, because G is where ABC meets A prime EF. I think we know that by inversion, because so we know those 4 points are cyclic, and it inverts to this line A prime IJ. So, but then we need to know that we do need G prime then. We can't get rid of it. We need to know that G prime. So we know the inversion of G prime lies on this line, but how do we know it lies on this line? Well, because this line JA prime inverts to, yeah, because JA prime inverts to this circle. So since yeah, I think we might have missed a step here. Whoops. Yeah, how do we know that G prime lies on this? Because this segment inverts to this circle, but how do we know G lies on this circle? because G lies on this circle. And yeah, I think we might be missing a step here. Let me see what time it is. It's already 10:30, so I think I'll move on to the next problem. But I think we're close. Like, I think that's interesting. Oh, yeah, I think we're close here, but let me see. So A double prime MS is cyclic, and G is the intersection of AMG and A prime EF. So maybe we can use the radical axis theorem to show that these are also collinear. I think that might do it. Because if we have the radical axis theorem on this, and this, I think that does it. Yeah. So I'll say and A prime G also passes through S. So yeah, if we use the radical axis theorem again, these are collinear, and so that would mean that this angle is also 90, and so G has to lie in that circle. I think this solves it. So I'm going to move on to the next problem, but I think this works. All right, it's a fun diagram. Okay, so let's try this problem. So we have two mixed linear circles. And